Okay. Okay, hello everyone. Welcome to our class. And hopefully you have scanned the QR code. And I've checked. I think almost all of you already taken the quiz. Okay, so I believe you already have the score directly, right? Okay, I will check later because I think some of the students might have I think different expectations for the score, so I need to recheck and check your answers. Okay. And let me know if you have any uh, technical difficulties using the platform. Please let me know. Okay. Okay. So for today's class, I would like to just continue uh, to work on the chapter 7. We discussed the integral by parts, right? So we will continue just that. Okay, I will start to open the notes. Okay, I think this is the last discussion. We have discussed about the integral by parts, and this is just to show you that uh, sometimes when you do the integral by parts, uh, it's important to write the the original the original integrals on the left side. It's important to see whether we have or we can do some simplifications after we are restructuring our integrals. For example, if we have this ex sine x, if we use integral by parts, this is our structure, right? The right one. But if we forgot to write the left one, and if we focus just going to integrate this this ex cos x, then it's going to be another structure. And if we are just forgetting ourselves to just stop here and reevaluate the equation, we might end up doing another integral by parts, right? Another integral by parts, and it will be another integrals, and we are keep repeating all the times. So we are going cycles. Okay? But if we look on the original equation that we have ex sine x, and it's the same ex sine x, we can simplify and we can group these integrals into one equations, and we can make it. We can move it to the left side, and simply we can divide all the equation by 2. Okay. It's the same way if we are trying to take this into our approach with DI, okay, DI table, DI method. We can stop this derivative up until when we have sine x here, because it seems that it is going to be the same equations with the original questions. So we can stop here and we can arrange the integrations, and we can also same thing as before, we can simplify and find the solutions. Okay. Another integral by parts that we can have is the tangent inverse. We can do the just as usual integral by parts, u phi, so integral u dphi equal u phi minus p du, integral p du. We can just do like this, or using the I table, okay, and then simplify it and restructure the integrations. Correct. Okay, now I want to start with for today's class is I would like to start with the let me check. Okay, if we set up integral of secant squared x dx, this is end up being tangent x plus c, right? Of course, right? Because we know that the derivative of the tangent is secant squared. Okay. Now, one special integration is secant x dx. Okay, how to integrate this secant x? Okay, one way to solve it is we can imagine if we have secant and we want to derive, okay, we start with some imaginations. We can imagine the secant x being derived, and we can then see the pattern. We derive this. This will resulting in secant x tangent x, right? Okay. And secondly, because we know that this is the derivative of the tangent becomes secant squared, okay, then if we can make up the secant and make it into either of the secant squared or secant x tangent x, then perhaps we can do something on the secant x. Okay, now let's imagine if we have secant x. First, the first method is we are going to multiply the secant x, okay, with a fractions. Okay. So of course, this fraction should be the same. It's like rationalizations, like we did in the limit when we learn the limit, right? So what will be the equations for the rationals? For the rationals, we would like to have the secants become secant squared. So when we integral, we get the secant, and we can get the tangent, and we would like to have another secant and tangent. When we integral, we have secant. So perhaps we are going to have secant x plus tangent x. This is also secant x plus tangent x. Because if you multiply this, this will be secant squared, and if we multiply this with the tangent, this will be secant tangent x, right? Okay, now let's multiply. Okay, now what's next? Okay. Because we know that this is the derivative, right? The derivative of secant and the tangent. Then if we are having secant tangent x, okay, if we derive this, this is perfectly will be the top equations, right? So if we derive this will be secant squared x or secant x tangent x plus secant squared x, right? Perfectly the same. So what I would like to suggest here is we are going to have use substitutions with secant x tangent x as u. Okay, and then we take derivative, and this will be let me write secant squared first, and then secant x tangent x, and then the x. Okay, so what we'll have here, I'm going to erase this. What we have here, integrations 1 over u du, and then this becomes ln, and then this we can write secant x plus tangent x plus c. Okay, and this will be important result to if we would like to elaborate more on the questions. Okay. Okay, perhaps up until here, is there any questions? Okay. So, by the way, what's your opinion about the quiz? Is it okay for you for the quiz? Is it difficult, or I believe most of you did a good job. Do you think it's difficult, your quiz? A little bit hard. I think Michelle, you get good. I think good score. Yeah, Helen also you got. I think pretty okay. Pretty okay score. Yeah, the quiz a little bit hard because I gave you like I think you can checking your notes and of course I need to set up the time because I want you to like optimize your your notes and your calculations. Okay, rather than if you are just doing it like if I gave you like with no time limits, then I wouldn't know whether you are really working on the subjects. So I think it's just like like a simple game, right? And I hope uh, in the future we can do some more more tests similar like that. And I think if you are doing like the previous one, like for Michelle and for Helen, I think if you do with this kind of effort, I believe, uh, and if you study more, I think you will become better in the future. Okay, let's continue. Okay, so from here, from the secant x, what I would like to bridge is if we have another variation in the secant. So if we have the secant cube, okay, this is also challenging. So what will be the integration? So of course, if you look the equations and if you think any integration that's available, readily available, we are not having any direct answers for the secant cube, right? But since we have in our backlog, we have the secant x that we have did just before, and we have also the secant squared that we can see some results from the secant squared. So perhaps we can take this into split the secant cube becomes secant x and secant squared x. Now this is another way to use the integration by parts. So integration by parts, you can also use it to separate like one whole power functions. You separate the power, and you will see some way to somehow you can simplify the equation, and maybe you can use substitutions or doing directly the integration by parts. That's also possible. Okay, now from here, what I want you to look at is we could have integration by parts by selecting. Of course, we will have at least two elements, right? The secant x and secant squared x. So, for example, if we are going to start with, I think the secant squared is easier to be integrated and becoming the tangent, and secant can be derived and become secant x tangent x, right? So we can have this as u, and this will be a dv. Or in our di table, I will just directly use di table. We can see that this will be secant x, this will be secant squared x. So we can integrate secant squared, become tangent x, right? And derive the secant x becomes secant x tangent x. Okay, and this will be having two structures. So we will have secant x tangent x, and then minus the secant x, and then tangent squared x dx. Okay, we have this structure. Now let's focus on this integral, the secant x and tangent squared x. Okay, what we can do here. Now we would like to see the tangent squared. Okay, focus on the tangent squared. Okay, now let me just write something that may be helpful for you if you are going to prove some identity in trigonometry. The first one is, I believe this is familiar with you, right? The identity. And let's divide by cos squared x. Okay. This will become tangent squared x plus 1 and then equal secant squared x. Okay. Now we have tangent squared x is secant squared x minus 1. Okay. This is if you are forgetting the identity. You can start from the sine squared plus cosine squared equal 1, and then you can divide by cosine squared to see the relation between secant squared and the tangent squared. I hope this is helpful. Okay, and then you can directly write the secant squared x minus 1, changing the tangent squared, and you get the results. The secant cube x dx is equal secant x tangent x. Okay, now this becomes secant cube x dx, and then minus secant x, or multiply with minus becomes plus. Okay, plus secant x dx. Okay. Okay, I think we can move the secant cube, right? We can move the secant cube, so 2 secant cube dx is equal secant x tangent x, and then we still have the secant x. So secant x is ln, right? ln secant x plus tangent x, and then we can have and plus 3. So we can have this for the secant. Okay, so from the I think the key is the secant x, finding the secant x first, and then don't forget to write the original equation so that you can see the relations between those two.
Hello, Professor.
Yes.
In this case, you only use integrate by part only one time or two times?
In this case, just one time.
Okay.
Just one time. The second one is from here. We can just substitute the tangent squared with the secant squared x minus 1. And then we see that we have this and this. The secant cube and the secant x. Secant x we already previously described, so we can just directly get the answer. And secant cube, we can move to the original equations, right? And we can solve the whole equation, right?
Oh, I understand. Thank you, Professor.
Okay. Okay. Now that is a little bit some example for secant and secant cube. So what I want to share with you today is basically we call it trigonometric integrals. Okay. Yeah, suppose the title should be at the beginning, but let me write this here, and start with before we move to secant and tangent, we can start from sine and cosine just to look on more details. So sometimes when we have sine and cosine, we can use some identity, okay, to correlate two of them, and then perhaps later on we can have some techniques of integrations. It can be substitutions, it can be integration by parts, depends on the case. Okay, for example, let's begin with the integrations of cosine cube x dx. Okay, now if we just look on the cosine cube, okay, perhaps this secant cube, the way that we did with secant cube, maybe it's helpful. So we separate this cube becomes squared and linear, right? So we can have the cos squared x and then cosine x dx. And then what's the next thing we can do here? The next thing we can do is we can look on the cos squared x, and we imagine that we have sine squared x plus cos squared x equal 1, right? So maybe we can exchange this cos squared x become 1 minus sine squared x, right? Why we are doing this? Because we know that we can have some connections, this 1 minus sine squared with cosine, because if we derive, perhaps we can have some if we let the substitution method, if we use the substitution method, maybe we can have some relation. So let's just write this first. So 1 minus sine squared x multiply cosine x. Okay. So if we let the u is sine x, then we will have cos x for canceling, right? Okay. So we would have right, integrations 1 minus u squared, right? And then cos x will be gone, and then the u. And then this will be perfectly becomes u minus u cubed over 3, right? Or in our case, this becomes sine x minus sine cube x divided by 3 and plus c. So this will be cos cube x dx. Okay, so one way to solve some trigonometric integrals is substitute or find the relations between sine and cosine. Usually the identity sine squared plus cos squared equal 1. And then if you look on this equation here, we can see some connection. So whenever you have a sine squared or cos squared and you have another element that is cos or sine, you can exchange this squared with u, and then you can finish off by cancellations for the other part, right? So what I hope you to gain from this example is not just the process, but the pattern, okay? The pattern that you are seeing. So it's not just on what is the solutions, but rather we see some connections and some patterns. Okay, whenever you see these connections, you have the squared and you have linear equations for the sine and cosine. You can have some cancellations through substitutions method. Okay. Okay, now the next example, we will have more variations in terms of the power. Right? and we will include sine and cosine in one equation. So perhaps let me give you an example. We have sine with 5x power 5, and then cos squared x dx. Okay, what we can do from these equations. Okay. We have sine with power of 5, and we have cosine squared. You can try several ways. You can try random things, but first it is obvious that if you are going to change this cosine squared, if you change this becomes 1 minus sine. This will be doing nothing, right? This will be no solutions, right? We don't have really any connections if we have just 1 minus sine squared. Okay. What we can do, however, so you see first, you see this is 5. It's an odd number, right? It is squared. Squared is an even number. And every time we have a connection between sine and cosine, it should connect through the even, right? This squared. Okay, so we have cos squared plus sine squared equal 1. That is our way to connect the sine and cosine through the identity. But if we have this with power of 5, okay, what we can do for this odd number is we are going to separate. Okay, just like we separate our cosine cube, we separate. Okay, and it's become having the even and then the other odd. So we can have this becomes so for example, let's try just separate this become this, right? And we can also make it clear the sine with power of 4 is sine squared x, and then squared, and then sine x. And I think you see where does it going now. Okay, so if we try to make it into the squared, so we will have sine squared x and then squared. Okay, and then we still have sine, but let me write cosine squared first, and then sine x. This is the same equations, right? And now we have cosine squared, we have sine squared. What's our goal actually? Yeah, this is not a random thing. So what our goal is, we have the linear one is just sine x. Okay, so look here for this one. The linear one is a cosine x, and we exchange the cosine squared becomes 1 minus sine squared, and this is cosine x. And the idea, okay, for this pattern is for the linear one to be cancelled. Okay, cancel, right? Cancellation. So this is true also for this case. What we are going to do is we are going to be having the sine x to be cancelled. So the idea is we are going to have the connection. So we need to have this cosine squared become the one that make the sine x cancel. But we are going to look on this cosine squared and sine squared. So perhaps if we are changing all to cosine squared, we can see some pattern. Okay, if you see already, then it's good for you. But let me just write to help you understand more what I want to say. So if we have this in terms of cosine squared and then squared. Now if we are going to focus on getting this, or not one, just cosine squared, then, or not cosine x, okay, then the du will be minus sine x dx. So this will be going to have minus, right? So we will have a minus because of the minus sine x, and sine x will be cancelled, right? Will be cancelled because of the substitutions method. This will be 1 minus u squared minus c squared, and then u squared, and then du. Okay, now we still need to expand and calculate the expansion here. I think it doesn't really matter, or it's not too difficult, right? So this will be 1 minus 2u squared plus u4, and then still we need to multiply with the u squared. So we will have u squared minus 2u4 plus u6. And I think because this is just a normal polynomial integrations, we can do this quickly. So we can write, and I think I can just make the answer here. Okay, so we can say that the integrations will result in, and we need to multiply with the negative. Okay, we need to multiply with the negative from here. So we will have a negative 1 over 3, and then u is cosine, so cosine cube x, and then plus 2 over 5 cosine with power of 5x, and plus 1 over 7, or not plus, it should be minus. Minus cosine with power of 7x plus c. Okay. Okay, so this is happen when you have the odd and even power for sine and cosine. And it's also happening if you are, for example, if we reverse this, it's become cos 5x and then sine squared x. Or even if you would like to try more power, or maybe just cos 3x sine squared x, still we will have a similar pattern and similar method. Okay, perhaps any questions? I hope at least clear. I don't want you to give you because in your textbook you will see like they give you like a formulations to see the sine and cosine. I don't think that's quite helpful, and it will force you to memorize things that it doesn't necessarily to be memorized. You can see this through the pattern. You can see this through pattern. One important thing eventually is if you are having maybe make some additional notes here. If you have integration sine squared x dx, okay, and if you have this, okay, or maybe integral cosine squared x dx, okay, how to integrate these two? So perhaps we need to have some simplifications, right? The sine squared, if you remember, okay, if we have integrations of sine x, it's easily we can write this will become the negative cos x, right? If we have sine 2x, this will be negative cos 2x over 2 plus c, right? And how to make sure? We can make sure from, if we derive this will be sine 2x and then multiply by 2 over 2. So we have that, right? Okay. Now what will happen if we have sine squared x and cosine squared x? Now because we did the sine to x, right? So we need to have at least this form can be written in. So we need to erase this power, right, this squared. One way to erase that is through these connections. So I will just write the original formula so that you can derive the formula from here. Okay? And if you would like to write down in terms of this is 1 minus sine squared x. So this will be 1 minus 2 sine squared x. And you will get that this will be your sine squared x. So by doing this, we can integrate easily because we know the integration of cosine to x, right? Okay. And some and the same way we could have for cosine squared x, we could have and exchange the sign. So we will have this connection and we will have the cosine squared x from here. Okay, I hope very clear. And from here you can integrate this sine squared x into this cosine squared x. So whenever you find this squared in the trigonometric, to solve the integral, you need to use double angle formula. Okay. Or you need to change the squared into the double angle. Okay. It's different case from what we have here. What we have here is we have two different formulations. If we are changing this to double angle, then we are going nowhere, right? We are just still stuck with this sign with power of 5. Still no clue here. So what we did here, we are going to see some connection between sine with power of 5 and cosine squared, and we get that from this. We can separate, becomes two elements, and then we can separate, become 1 cos squared x like this, and then later on we can simplify and cancel the sine x with the u substitution. Okay, the different case from the double angle. But whenever you have a single integral, it's having the sine squared or cosine squared, you can have double angle. What about sine with power of 4? It's the same. So whenever you have any even power function for sine or cosine, the single variable, single integrations. For example, sine with power of 4. This is also using the double angle, but your double angle will be having a square. So this is simply, we are saying that this is equal with this, right? So we substitute, we exchange this, and so let's say we have this, and then we square. So we expand the equation, and later we will have another like cosine squared 2x, right? We need to do another double angle to make it into cos 4x. Okay, and that's how we solve. And if you are having more and more, for example, it's not like only sine with power of 4. Maybe you have some multiplication of that. It's also the same, and you will have like more double angle formula to come. Okay. Okay. Any questions? Okay, question? Okay, if not, let me continue. So this first part is about sine and cosine for trigonometric. The second part will be about the secant and tangent, because that is the second identity that we will observe. Okay, I will move to next slide, to the next notes here. So the second one will be about secant and tangent. So let's start with just example. Okay. So tangent 6x, and then secant, and then 4x dx. Okay, now what we are going to do here. So the key here is to see some connections between the tangent squared x plus 1 is secant squared x. This is the connection. So we are going to see these connections and how we are going to deal with the question. And use the fact that if you derive the tangent, this will give you secant squared x. So perhaps our goal is to make the tangent x in our solution here to become the secant squared x. So if you write the equations, and if we try to make these connections with tangent squared plus 1 here, then we need to have the secant squared, and we get the secant squared from secant 4. Okay, so perhaps we are going to separate, become secant squared x dx. Okay, and then later on we could exchange one of them. Right? And because we know that the derivative of the tangent is the secant squared x, so the secant squared x will be a target to cancel. So we are going to cancel the secant squared x. And if we let the u is tangent x, and our d will be secant squared x dx. And we are going to cancel the secant squared x, right? So we will have integrations u6 and then u squared plus 1 and then du, and we are going to get u8 plus u6, right? So we will get 1 over 9 u9 plus u7 over 7. So we will get, or maybe directly we can write 1 over 9, this is tangent with power of 9x, plus 1 over 7 tangent with power of 7, and then plus c. Okay. Okay, that's the first case. The first case is directly changing the secant square with the tangent square plus 1, and then we see connections, and our goal is to cancel the secant squared x. That's the case for this example. Okay. And you're going to see this pattern from the question itself. You see that we have tangent with power of 6, secant with power of 4. It's an even number, right? Now the second example for the tangent and secant, what if it's not an even number, but it's an odd number for the power? So let's say we have tangent with power of 5 and secant with power of 7. And of course, if we are trying to do the same thing with the secant squared here, and if we take this become secant 5 and secant squared, this is still difficult to control and to integrate, right? So it's not the best way to look at. So what's the deal uh, for this case? So let's separate. Okay, let's separate because remember, aside from the tangent, if we derive that becomes secant squared. Aside from this, we also have the secant itself, right? And when we derive, this will be secant x tangent x. So what I want to say is, if we have this tangent secant variations, we are going to see some cancellations on this secant squared. This is our target to cancel. Okay, target to cancel. And this, okay, because we know that we can later substitute the secant, so we can cancel the secant x tangent x, and that is what will happen here. Okay. So this will be, we can write tangent 4x secant 6x, and then we can write secant x tangent x dx. Okay. And what's next? What's next is we are going to look at this tangent with power of 4, okay? Because our target is we are going to substitute the secant, then we are going to exchange the tangent into secant. Okay, our target is this. Okay, we need to cancel this. Okay, so we're going to let the tangent become a secant squared x minus 1 and then squared. Okay, so we can have, let me just write another one here. This will be secant squared x minus 1, secant with power 6, and then secant x, tangent x, dx. Okay, I think we can directly use these substitutions. And we can see that we can cancel this part, right, with this. So we are going to have, let me just write maybe over here, u squared minus 1 squared, and then u with power of 6. So we solve this first. So we'll have u10 minus 2 u8 and plus u6. And this becomes, or maybe let me write to the right side. This will be 1 over 11 secant 11x minus 2 secant 2 over 9 secant 9x plus 1 over 7 secant 7x plus c. Okay, alright, so the idea for secant and tangent variations in our integral, we need to focus on finding the secant squared x or secant x tangent x. This is our two targets, our goals, that we are going to cancel these two and we can use substitutions method. Okay, I hope that's clear. Okay, if you're still having any confusions and not really clear what's happening here, let me know. Okay. Okay, any questions? So far it's okay, or a little bit confusion? Okay, let's we'll continue. Okay, one way to solve the trigonometric integrals is using some we call this, for example, if we have sine 4x and cosine 5x dx. Okay. Of course, if we look on these integrations, we could see that we have two elements, sine 4x and cos 5x, and we see that we can derive and integrate both of them simultaneously, right? So we can just use integral by parts if you would like. But if we are remembering some identities that we have, okay, if we have sine A cos B, this will become how, and then sine A minus B, and then plus sine A plus B. Now we can solve this, and this becomes integrations half, and then sine A minus B is become minus x, and then plus sine 9x. And then this become dx, and still we have to solve this half, and then this will be negative sine x, negative sine x plus sine 9x, and then dx. And this would result in negative sine becomes cosine x, and sine 9x become negative cosine 9x over 9, and then plus c. I think we can also solve through this these formulations, the identity. We could have another one, sine A sine B, right? If you remember, this will be cos and minus cos A plus B, right? And then cos A cos B, this is still the same, cos and plus, right?
Professor,
Yes.
what is this called in like the name of the formula, so I can like study
Oh,
for it
the
further
name?
about it?
You mean
Yeah, yeah, this one, like the
uh,
sine A cos B something.
you can say the product identities. You can say the product identities
Okay, thank you,
right
Professor.
here. Product identities. Okay. But if you maybe if you forget to write the identity, it's still okay. You can just still do the integral by parts, and I think not really that long. And sometimes in integrals, because you have several techniques, several methods, sometimes the result seems different, but they're actually the same. And what makes the same is because we still have the plus c. This will be make our differences becomes equal. So perhaps we have I don't have any example now, but let me just check in another lecture. We'll check some example that might have different. It seems different solution, but it's actually, if you look because of the plus constant, we can say that it might be the same. Okay, but for example, you have this sine. Okay, you have the sine 4x and cos 5x, and this is the result. Maybe you get the different result with another method. So you have this different result, but still it's have the plus c, right? But the question is the c1 and c2 the same? It's not the same, right? Okay, let's make these two results equal because of the constant. That's just some notions to let you know. Okay. Okay, that's the trigonometric integral. Okay, for most of the part. In the next section, this will be discussing on substitutions method, but with trigonometry. We call it the trigonometric substitutions. Okay, let me move to the next sections. Okay, trigonometric substitutions. Perhaps to make it more understandable, we could start with the basic identity that we have from the previous trigonometric integrals that we have. The first one is just the sine squared x plus cosine squared x equal 1. Okay, and then the other one will be tangent squared x plus 1 equals secant squared x. Okay. Now what's the deal with these two identity? Now if we look closely, the first one, we could have sine squared x is equal 1 minus cosine squared x, and then cosine squared x is equal 1 minus sine squared x, right? And the tangent, we could see that the tangent we could write in terms of secant squared x minus 1. Okay, so the deal is what we are going to do in trigonometric substitutions. Okay, so in substitutions method, we substitute u, right? U as one element of our functions, right? In trigonometric substitution, what we are going to substitute, instead of u, we substitute with trigonometric equation. For example, if we have integrations and we have a 1 over x squared and then x squared minus 9. If we see this equation, the variable, what we are going to do next is we are going to substitute the x in our equation here becomes trigonometric function, which means the very form that you have, this, and this will be the key. So whenever you have any 1 minus, let's say, x squared, you can directly think that maybe we can change this x into sine or maybe cosine. And if you have seen this x squared minus 1, perhaps this will be going to be our secant theta. Now, if we have this, okay, forget the dx. Now, if we have this x squared minus 9, so the idea is we need to exchange the x into our trigonometric function, which means we can exchange x. Perhaps this will be a secant, right? Secant theta, but we still have 9 here, okay? So perhaps we need to square root the 9, and this becomes 3, okay? So when we do this 3 secant theta, then we could have, if we square, or maybe we write in the other part, if we write it's 3 secant theta squared and then minus 9, so we will have 9 secant squared theta minus 9. This will turn out to be our tangent, right? So, or let me write simply becomes that. So we could have this as 9 tangent squared theta, and 9 tangent squared theta is still under the square root, right? Square root of this one here. So we will have 3 tangent theta. Okay, so let me just write here, at the description here. So if we let the x equal 3 secant theta, and the dx, if we differentiate, this will be 3 secant theta tangent theta d theta. Okay. Now, if we have integrations, wait. Okay, sorry. So if we have this, the dx will be 3 secant theta tangent theta d theta, and then we still write this x squared is 9 secant squared theta, and the square root of x squared minus 9, this will be our 3 tangent theta from here. So we write 3 tangent theta, and we can solve and cancel some part of the equation, and still see that this will be 1/9, and an integral 1 over secant is cosine theta d theta, and we still can take this integral easily. This will become sine theta, right? And it seems that we are going to stop here, but remember, we are at the beginning it's about x, and now it's a theta. Now we need to revert the theta back to x. How? We can start with the triangle that we made. We could start with, imagine from the first one that x, so x is 3 secant theta. Or we could say that the secant theta is x equal 3, or cosine theta is 3 over x. So cosine theta is 3 over x, and this part is x squared minus 9. Okay, so from here we get that the sine theta is square root of x squared minus 9 over x. So that will be our solution for this one, over x, and then don't forget to plus c. So I always avoid adding c at the beginning, at the middle of the process. I will just add lastly, like when you already deal with all the calculations, at the very end just plus constant. Okay, this is my tips for you. If you add plus c at the middle here, it will make the equations will be not consistent, because if you imagine this c and this c will not be the same, right? If you not really know what I'm talking about, I think we can just ignore that. But just let's say we are going to have the constant at the very end. That's for sure. Okay. Okay, that's one way. So the idea of the trigonometric substitutions is to substitute the sub variables with trigonometric functions. Okay, this is case 1. In case 1, we are having the secant x. So we have the secant squared x minus 1 as our identity to exchange. Okay, now the second case, we have integrations x cubed (9 minus x squared). Okay, before we did the trigonometric substitutions, we can take another method if you would like, that usually we can solve. Okay, so one particular or one obvious obvious reasons we are using the trigonometric substitutions, if you look at the equations, you will see that it has the square root. Okay, it has the square root. Okay, the square root. Okay, now if you look here, we have the 9 minus x squared. So 9 minus x squared, if you look here, our candidates is the first and the second one, right? We have the 1 minus cosine squared x or 1 minus sine squared x. So we could have sine or cosine as our substitution. Okay. So we could have from this one, let me just write using sine. Okay, so x, let's say we have 3 sine theta. Okay, so that when we are doing the 9 minus 3 sine theta squared, this become this, and we can have 1 minus cosine squared theta, which is the sine squared theta. Okay, so we are going to have that, and we have the derivative will be 3 cosine theta d theta. Okay, now we could substitute the 3 sine theta directly to here, and then this will be square root of 9 sine squared theta, and dx will be 3 cos theta d theta. It seems long, but that just takes time. So it takes time to solve this. So let's start with this. Maybe just write 3 sine theta cube, and then, or maybe let me write more clear that this will be 3 cube, and this will be sine cube, and this will be 3 sine theta, and then 3 cos theta d theta. Oh wait, should be, this is sine, it should be cosine. Sorry. Should be should be sine and then cosine. So this will be 3 cosine theta. Okay, let's combine 3 and become 3 power of 5, and we still have sine cube theta and then cosine squared theta theta. Okay, now remember, this will be results in trigonometric integral that we discussed before. So idea here is to separate, okay, to separate this sine becomes sine squared theta and sine theta, and sine squared becomes 1 minus cosine squared theta, and we have cosine squared theta and then sine theta, right? Okay. Okay, now we could have another substitutions. So we need to substitute the cosine theta to cancel the sine, and this will be having a negative. Okay, now we still have this, so we can cancel this and take a negative in the front. Then we have 1 minus u squared and then u squared. Okay, so we'll have negative u squared, negative u4. So we could have negative 3, 5, and then this will be 1 over 3. U is cosine cube theta, and then this will be minus u5 is cos 5 theta, right? Okay, still we have, let's exchange this and make it into more positive. So I exchange the negative part, rewrite into positive, so it becomes this. And still it's not complete yet. We are still having, maybe going to put here. Okay, now let's do some triangle. So theta, so sine theta is x over 3. So x over 3, and this will be 9 minus x squared. Okay. So our cosine theta will be square root of 9x minus x squared over 3. So we could exchange all 1 over 5 with these equations. It seems really complicated, but it's okay. Still plus c. I think if you want to cancel this 3 5 with this, I think we still can do that. So we could simplify this, becomes to 1 over 5.
Professor,
Yes.
I want to add something.
Mm-hmm.
Can we use another method to solve this one too, or just to solve like this question? Like method too, right?
Yeah. I think so far probably no. Yeah, I think, but let's see if we are trying to do some integral by parts. I think still difficult. If you are going to have x cubed, or maybe you having the let me check quickly just to see whether it's possible. If you derive, becomes to Yeah, I think it's becoming more ugly. And this will be minus, minus. Yes, we were stuck here, so I don't think integration by parts is helpful.
Oh, okay.
Yeah, I think.
So we have to solve by this method.
Yeah, I think for now this method. Okay, unless I find another way.
Okay, thank you, Professor.
Yeah. It seems really complicated, but if you are following the trails from how the behavior. So if you have a constant minus a variable squared, and it's under the square root, uh, for obvious part and for most of the cases, you are going to just take the substitutions. So you take the trigonometric functions into our variable x.
But Professor, how do we know we use sine or cosine? Like in this case, you use 3
Here.
sine theta,
Yeah,
right?
yeah, it's from here. So actually, you can also use cosine to solve that one. It's so whenever you have a constant, so you see a constant minus a cosine squared, right? Constant minus sine squared. So you can use cosine or sine to change the function. So whenever you find something, maybe 4 minus x squared, so you could change the x into either 2 cosine theta or 2 sine theta.
I got it, Professor.
Yeah, both work. So
The answer is the same, right? I mean,
yeah, should be the same. If there is a little bit difference, that's still okay. That's still okay.
Oh, thank you, Professor.
You could also it also works if you are trying 3 cosine theta here. Okay. And it will be, I believe the answer will be not in the cos but in the sine. Okay. But you can change later to the x to make sure that it's the same. Or still, if it's a little bit different, still okay. For me, as long as it's consistent and correct, still okay.
Okay, thank you, Professor.
Okay. Oh yeah. The so this is the first case. This is the second case. It's the second case. So we have the first one is we have the secant minus 1. So you have a variable minus constant. You have constant minus variables, and also this one plus. You have a variable plus a constant. That's the third case. So you have for these two cases you have minus, right? You have minus either constant minus variable or variable minus constant. The third case will have a plus, a variable plus a constant. That we are going to focus on that third case. So when we have the plus, then we can change the variable into tangent. Okay. Okay, let me go through next section. We are going to have Okay, we are going to have the third case. So I'll just give you directly the examples and see how we can use some substitutions for a trigonometric directly. So x cubed so this is the third case. So we are seeing this part, we have a plus between the variable and a constant. And remember that this trigonometric substitutions is not always works. Okay, if you see any square root and then you see some squared plus something here, it's not always works. Okay, so you need to see in more general. Okay, so perhaps you can try the integration by parts. You can try the substitution method, but usually when we have an obvious choice for trigonometric substitutions, we are looking at, first we could try substitutions, but we are looking at this is x cubed and this is x squared. If this is just x, perhaps it's substitution is easy, right? If we, for example, just x, we could say, okay, we can substitute, right? We can cancel the x later because we have the x squared at the bottom, and we can differentiate, becomes 2x, right? But it's not like the previous one. Also, you cannot really see, for example, this one, we cannot really substitute, right? This is also, we cannot substitute to cancel the x cubed, okay? Because the variable outside the square root is higher than the inside. Then we cannot really use this substituting. So we can see the trigonometric substitutions, and perhaps we are thinking on using the tangent squared x, because it will goes to secant squared x if you plus a constant. So perhaps we could start with taking x equal 3 tangent theta. Okay, because if we have 3 tangent theta and the square plus 9, this will be equal 9 tangent squared theta plus 1, right? And this will be equal to 9 secant squared theta. Okay, now this integrations is becoming, we have 3 tangent theta and then cube, and then this will be having 9 secant squared, so we have a 3 secant theta because of the square root, and the dx will be 3 secant squared d theta. So 3 secant squared d theta, and then we can cancel. So we have 3 cube and then integrate tangent cube theta secant theta, and we are going to remember what we did last time in the trigonometric integrals. We have secant and tangent. We have both are odd number. So what we are going to do, we are going to separate the secant and tangent. So we are going to have tangent squared and then tangent theta and then secant theta d theta. Now the idea is the tangent secant, we are going to cancel them. Okay, so how to cancel them? We have to have the secant, because d dx sec or d theta secant theta is secant theta tangent theta, right? And how we are going to do that? From the tangent, we have the secant squared theta minus 1. Okay, so let me write completely. 3 cube, or directly 27, is secant squared theta minus 1, and then secant theta tangent theta d theta, and then take u is secant theta, so du will be secant theta tangent theta d theta. So we can completely, like, the whole thing here becomes du, right? and this will become u squared minus 1, and we could get the this become u cubed. U is secant, so secant theta cubed and divided by 3 minus secant theta. Okay, that's our supposed to be the solutions, but we need to remember that this is not the solution that we want. We want the solutions that is based on this triangle. So we could have tangent theta is x over 3 from here. Okay. So theta is there. Maybe it's right. So x and 3, and this will be x squared plus 9. And secant will be square root of x squared plus 9 over 3. So we are going to get so this will be 1 over 3, and then secant theta will be square root of x squared plus 9 is 3 minus, okay, and this is plus c. So we get this will be 27. So this will be 1 over 3 square root or x squared plus 9, 3 over 2 minus 9. Okay, I think this is the answer. Okay, 3 cases, and hopefully you can get to know on how we are going to have the trigonometric substitutions. Okay, maybe another example. Okay. Another a little bit more difficult example. Let me just take for you. Okay, so this is the basic 3 cases that we might have or we might encounter in trigonometric substitution. So perhaps we could see more examples. Okay, maybe I will give you at least two examples, or maybe 3 if we have time. Maybe 2 first. The first 2. Okay, the first one is a little bit complex here. 0, 3 over 2 square root of 3 and x cubed. Okay, just to look at the equation first. Okay, no need to annex. Okay. Just look at the equation first. and then relates these equations to trigonometric substitutions. Could we do something about this? Can we do something about this? Okay, perhaps the one that might intimidate your mind is this 3/2 here, right? But let's just think clearly, okay? Slowly relax. We can write the 4x squared plus 9. Okay, we could write, because it has square root, okay, we could have write maybe this. Okay, we can write like that, or even we could write this. The cube is outside, also fine, right? I think better this form. Better looking at this form. So still we have the square root, okay? So the equation is under the square root, in which if we are going to take closer, we still not be able to use some substitutions here, right? Because it's the outside variable will have it's having a higher power, right? So we are simply just the only options, it seems that we are taking the trigonometric substitution. Okay. Now we have 4x squared plus 9. Now it's not just x squared plus 9 that you can directly say that this will be tangent 3 tangent theta, right? But we have 4. What could we do here? What could we do? So we need to do something on the x so that we could cancel 4 and becomes 9. So we would like to have, for example, we have plus, so the x should have at least a tangent theta, okay, for one element. Another element that we could have is, if we have 3, then it will be easy 9, but we still have 4. So we need to cancel 4. Well, what could we do for canceling 4? We need to divide by 4. So we have 2. Okay? So when we deal with this, so 4 and 3/2 tangent theta, and then square, and then plus 9. This will turns out can be cancelled. So we have 9 tangent square theta plus 9. Okay? And then from here, we get that this will be equal to 9 secant square theta. Okay? And this will be, if we square root this will be 3 secant theta. Okay? Now let's try to put into our equations here. And since we have this x, okay, then we are going to change the endpoints. Don't forget to change the endpoints. So if we are having this x and we are changing all within the theta, then we are having the dx is secant squared theta d theta. Okay, so so 0 is 3/2 tangent theta, so theta is 0, and 3/2 squared 3/2 tangent theta. So cancel, so tangent theta is square root of 3, so theta will be pi/3, right? Tangent 60 is square root of 3. So we could have the integrations become from 0 to pi/3, and x cubed becomes 3/2 tangent theta cubed. And this will be this is cube and 3 secant theta, right? From here, and dx will be 3/2 secant squared theta d theta. Okay, we solve slowly one by one. This will be 27 over 8 tangent cube theta multiply with 3 over 2 secant squared theta. This will be 3 cubed is 27 secant cube theta. We can cancel. 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 So we could have 3 over 16, right? 3 over 16 tangent cube theta secant theta d theta. Okay, now we could also see the connection here. We could have this and divide by this, right? So we could have divide this and becomes cos squared. So we could have the sine cube divided by the cosine squared theta d theta. And then still not yet finished. We'll write here 3 over 16. Let me separate the sign. Okay. And this will be 0 pi over 3. And sine squared will be 1 minus cosine squared over cosine squared theta sine theta d theta. Okay, I think we can take substitutions. Take substitution of cosine theta, and du will be minus sine theta d theta. So we will have minus 3 over 16, and this will be 1 minus u squared over u squared du. And all right, we need to change all terms theta. So u is first is cosine 0 is 1, and cosine pi over 3 is half. So we could exchange 0 become 1, pi over 3 becomes 1 over 2. This will be 1 minus u squared du. Okay, now what's next is we could just separate this will be 1 over u squared minus 1, right? And du. Okay, now integration of this become 1 minus 1 over u, and this will become minus u. And because it's all negative, we could write the positive 1, and then this will be u plus 1 over u from 1 to 1 over 2. So we could have half plus 2 minus 1 plus 1. So we could have half, so 3 over 32. Okay, it's quite long. Okay, a little bit complicated, but the idea here is just showing you that the variable that you are going to substitute, it doesn't always a perfect x squared. It can be also like this. For x squared, you can substitute with 3 over 2, for example, here, 3 over 2 tangent theta. Okay. Any questions for this one? It's quite long and pretty tedious. Okay, you need to substitute and then use the substitutions method again at the near the end, and then you get the result. I'm not sure if you are getting this question, how much time you will need to solve this and getting the direct answer. I think more than 10 minutes, right? Should be more than 10 minutes. Do you think so? Okay. Yeah, 15, I think. Probably 15, 20. 15 minutes, 20 minutes. But I think if you focus, I think 15 can be done. Okay. Okay. Okay, because I was thinking another platform that can be done for online testing. That is especially for mathematics or calculus. We can still doing it. Okay, I choose the platform that you have work on, the quizzes, because the quizzes for the math equations, it's easy to be written down, and they recognize the LaTeX language for programming, and for me it's easier rather than I think another one you need to write on another words or documents. You take a screenshot, put the image. Yeah, sometimes it's good, but I think not really in terms of saving the time. I prefer the quizzes for preparations. Okay, I think one more just short example. Okay, what can we have in terms of the questions? Another example that can be done is, for example, we have integrations x over square root, and then we have 3 minus 2x minus x squared dx. If you see from this functions, perhaps you see that perhaps we need to substitute here, and it's become 2x minus 2x minus 2, but it doesn't really correlate with x, right? We cannot do anything about that. So what can we do to solve this? What can we do is we are going to try some simplification from this 3 minus 2x minus x squared. Okay, let's try to do some if we look on 3, if we take minus x squared plus 2x, if I write like this, okay, perhaps if we are going to make it into a full perfect complete square, then maybe we can plus 1 here, right? And then minus 1 outside. So then this will be why minus, so it should be plus. So we have 4 minus, this will be x squared, or x plus 1 squared. Okay, now if we have this, then we can write this in terms of 4 minus x plus 1 squared. And then for our substitution here, for trigonometric substitution, we can imagine this x plus 1 squared as our trigonometric substitution. So we could have, for example, let's say we take x plus 1 as u. Okay. So du is the x, and x is u minus 1. So we could change this into u minus 1 divided by square root 4 minus u squared and then du. And I think from this variable u, we can take the u squared, and we can take the u as 2 sine theta, so that we can have integration square root of 4 minus 4 sine squared theta, in which this will be a 4 or 2 cosine theta, right? So directly we could say that this will be, if we change all, u becomes 2 sine theta minus 1, this will be 2 cos theta, and du will be 2 cosine theta du. And we can cancel this, so we have 2 sine theta minus 1. We could take the integrations, and I think we could directly integrate. But remember, we have to go back to x, so we need to have from the triangle, we say that this is theta. So sine theta is u over 2. So u and 2, this will be 4 minus u squared. Okay, so the result will have u, and u is x plus 1. So we need to change back to here. Okay, I will just leave this for you to solve. Okay, I give you some guidelines here. Okay, and that is the trigonometric integrals and trigonometric substitution. Okay, maybe questions? Okay, if you have any questions. I know that it's becoming a little bit more advanced and difficult, but I hope you can get some ideas or insight from what we have. Okay? At least not memorizing the steps. Okay? Not memorizing the steps. That's not the way. But look on the pattern. Observe the pattern. That's the key. Okay. I think if we don't have any questions, we will see you later. Oh, I forgot to mention, no class this Friday. Okay, no class this Friday. So I will just add additional videos later on. Okay, so no class this Friday. You can watch the additional videos, and maybe giving you some homework to be done. Maybe giving you practice. Okay, and then I believe that will be for Friday class. Okay, QR code. Okay, if you don't have any questions, then that will be our lecture. So thank you for joining, and I believe we will see you next week, Tuesday. Because we've done chapter 6, perhaps not next week, maybe next 2 weeks, I will prepare another quiz for you for chapter 6. Okay, I hope you can prepare that. Okay, thank you everyone.